Welcome. In this video series, we are going to cover all different types of logic gates. This video covers NOT and buffer. You can find the playlist in the description. So as you know, computers work with ones and zeros. And to represent ones and zeros, we have some high voltage range and some low voltage range. Two different range type exist. We have TTL and we have CMOS ways to do it. So as you can see, CMOS high range and low range are like this, and TTL ranges from 2 to 5 and 0 to 0.8 volts. So this would be a 1 and this would be a 0 in the eyes of the computer. And so to physically build these things, BJTs are used for TTL and MOSFETs are used for CMOS. In the previous video, I showed how to use BJTs as switches, which is going to be helpful for explaining this video. So we have NPN and PNP types. Then for MOSFETs, we have N and P type MOSFETs. There are some other types of MOSFETs as well, but we are not going to dive into those. Actually, we are not even diving into CMOS at all. We are going to show how to build logic gates from BJTs. And here you can see internally how an NPN and how the MOSFETs are made. But we are not going to discuss this in this video. And here you can see older stuff use TTL technology and newer stuff use CMOS technology. Moving on, we are going to cover 8 different logic gates. So let's start with NOT gate. NOT gate basically works by inverting whatever you put in the input. So a 0 goes to 1 and a 1 goes to 0. And here's how to build one with an NPN BJT. Like I said, if you haven't watched the previous video, you wouldn't understand why we chose these resistor values. But just to briefly explain what they are, this would be our load, but we are using it so that it's limiting the amount of current going through the circuit. This one is the base resistor. It limits the amount of current going to the transistor base. And this is our pull-up resistor. So when the input is like the switch is not connected, the base is not floating. You might also see my note about the resistor. The load resistor should be on the collector side. As you can see, the NPN collector side is here. And for the PNP as well, which I will show later on, the load must be on the collector side. Otherwise, it will create a situation where a transistor will partially turn on. I will show the proof of that later on. And so let's begin. So here we have two different sides. We have the NPN and we have the PNP version. We are going to cover that afterward. So right now I'm giving 5 volts to the breadboard right here. Okay, let's turn our multimeter on. And as I shown in the schematic, we are going to measure just right below the resistor on the collector side. It would be right here. And the negative side of my multimeter, I'm connecting it to the power supply. And here we are reading right now 0 volts. So some videos you might have seen before that they use an LED to show if the logic is 1 or 0, but you shouldn't really look at the LED if it's on and off. The computer doesn't look if a photon is hitting our eyes or not. It looks at the voltage. And so I'm never going to use an LED to show the logic here. We are always going to look at the voltage and decide whether it's a 1 or 0. So right now we are getting a 0 because we are giving a 1 to the base of the transistor. So our input is 5 volts and we are getting 0 volt as an output. It's almost 0 because we have some voltage drop across the transistor, but like I said in the TTL logic, it's 0 to 0.8 volts. So this is considered as a 0 on the computer's eye. And if we change the input to 0, we are going to read 5 volts. So our transistor turns off and therefore the ground is not connected to this location. But when the transistor turns on, when we give 5 volts to an NPN, the current flows from here, and then the current flow from here also gets activated. So then the ground, 0 volts here, gets connected, like shorted to this location. And so we see something like 0 volts. Okay, let's look at the PNP now. This time our pull-down resistor is now a pull-up resistor. And this, as you can see, is connected to the ground. So when we close the switch, we give 0 volts to the transistor, which turns it on, like allows the current flow. And our resistor is now on the bottom. As I said, it must be on the collector side. And the collector on the PNP is on the this side. You can imagine the collector being always the side that doesn't have the arrow. And so let's give power to the next circuit and read from the output side I'm showing in the schematic. And as here you can see, we are reading 0 volts because actually we have a pull-up resistor. So now the transistor is actually off. It's not allowing any current flow. And because there is no current flow, our 5 volts right here is not being shorted to the output. So we see 0 volts, from here. As you can see, if I put it on 1, 5 volts, nothing happens. If I put it on 0 volts, we are getting 5 volt. It's because the 5 volt here gets shorted here. Moving on with the buffer gives exactly the same input as the output, so it doesn't change anything logic-wise. So you might wonder why it's useful then. It's useful because it adds a delay from input to the output. So if you give a 0 coming from a 1, this 0 takes some time to appear here. In my case, here, I measured the delay with an oscilloscope, so it's 3 microsecond. It's tiny, I know, but in your application, if you need more delay, then you can just keep adding more and more transistors here and add more delay. Another useful thing with the buffer is that the gain is quite high. So you give a tiny current here, you get a huge current passing through here, let's say maybe 15 times more. And this 15 times current gets multiplied 15 more times here, so you get 15 square current passing through here. So it has some interesting uses. And here you can see our output was normally here for an NPN. But that output is now connected to the base of a second NPN transistor. So when we get 5 volts here, then the current flows, and then we have some other current passing through here. And now shorting the ground to this location. And in order to get 5 volts here, so that means our output must be 0 volts, so that this NPN doesn't turn on and short this location to the ground. So this is now 5 volts, and then we turn that one on. But if the transistor is getting 5 volts from here, it turns on, and we are shorting this location to 0 volts. So then this transistor turns off, and this stays at 5 volt, getting it from there. And to see that, I again connected my multimeter, and I turned on my power supply. When we are giving a 1 as an input, we are getting 5 volt. When we move it to 0, we get 0. As you can see, I didn't even have to connect it here because we have a pull down resistor, and it is right here. And the PNP version of this is not much different. I'm again measuring from where it's specified in the schematic, which would be right here. And when we give 0 volts, we get 0 volts as an output. Our input is right now here. And if I give 1 volt, and I didn't have to put it there because we have a pull-up resistor, so it doesn't change anything, we get 5 volts as an output, so it's a 1. And what was changed, that our load resistor was now on the other side. We have now pull-up resistors, and so our output in this location was connected to the base of another transistor, which would be the other PNP type. And when we give 0 volt here, which would be closing the switch, this PNP transistor turns on and it allows the current flow. So it's shorting this location to the top, which is 5 volts. And then when the other PNP sees the 5 volts, there is no current flow. So then it turns off. It doesn't allow any current flow. So the ground side is right now being seen, and it doesn't get shorted to the 5 volt side. And you might wonder why there's no voltage drop across this resistor when it's right now connected to ground. It's because there is no current flow in the output. Okay, let's continue with NAND. You might wonder why we didn't start with AND, but rather with NAND. It's because in the AND situation,